Let's talk about solutions to homogeneous linear systems of differential equations with distinct real eigenvalues. For the linear system dx dt equals negative x plus 1y, dy dt equals 7x plus 5y, compute the eigenvalues and the corresponding eigenvectors and find the general solution. First, let's find the eigenvalues of negative 1, 1, 7, 5. We know how to do that. So here's our matrix. We look at the determinant of a minus lambda I. In other words, we put lambdas along the diagonal and take the determinant of that. I'll multiply it out. Minus 1 minus lambda times 5 minus lambda minus 7 equals 0. In other words, negative 5 plus lambda minus 5 lambda plus lambda squared minus 7 equals 0. That simplifies to lambda squared minus 4 lambda minus 12 is 0. In other words, lambda minus 6 lambda plus 2 equals 0. So it looks like the solutions are lambda equals 6 and lambda equals negative 2. Okay, so the eigenvalues are lambda equals 6 and lambda equals negative 2. If you were to find the corresponding eigenvectors, you'd find that they're 1, 7 and 1, negative 1. Okay, here's how that's going to help us to find a general solution to that system. Suppose matrix A has a real eigenvalue lambda with corresponding eigenvector v. Then the linear system dy dt equals ay has solution y of t equals e to the lambda t v. Moreover, if the eigenvalues of A are the distinct real numbers lambda 1 and lambda 2, with corresponding eigenvectors v1 and v2 respectively, then the general solution of the linear system dy dt equals ay is y of t equals k1 e to the lambda 1t times v1 plus k2 e to the lambda 2t v2. You'll see in a moment how we apply this. So again, this is just a reminder. This is the statement. That's what our solution is going to be. Our eigenvalues are lambda equals 6 and lambda equals negative 2. These are the eigenvectors. So let's plug these in. The general solution is going to be, again, for the first eigenvalue, lambda 1, let's plug in 6. And for the second eigenvalue, lambda 2, we're going to plug in negative 2 because those are our two eigenvectors. Next, for the first eigenvector, we plug in 1, negative 7. For the second eigenvector, we plug in 1, negative 1. And that's it. That's our general solution. So in other words, you can just read across the top because the solution is really a vector. So we have x equals k1 e to the 6t plus k2 e to the negative 2t. Y equals negative 7 k1 e to the 6t minus k2 e to the negative 2t. This is what we do when we have distinct real eigenvalues. If we repeated real eigenvalues or complex eigenvalues, then we use a different approach. When I say repeated real eigenvalues, I mean if we have 2 and 2 both as eigenvalues.